Okay, thanks very much for the invitation and for this opportunity to present this topic. In this mini course, I'll focus on discussing B-model. And here's the rough plan. So we're going to start with some classical geometry of B-model on Calabi-Yau manifold. Then we're going to move on to quantum aspect. And after this, we're going to discuss a little bit about this open-close B-model and large N-duality. And if time permits, I will try to say a few things about worship B-model. So I'm not sure whether we're going to have time for this point, but let's see. Okay, so first, let me give a quick overview, some introduction to this topic. And this arises from the study of so-called mirror symmetry. And actually, this symmetry is a duality between superconformal field theory arising from physics. And then we have actually a mathematical prediction on this duality between two branches of mathematics. One of them is about, let me say it this way. It's actually a 2D theory, so roughly speaking, they describe the geometry of mapping space. Say from a surface to some target, let's call this one X. And then there are two ways of encoding some geometric data and the invariance. One is related to symplectic geometry. And usually people call this A-site or A-model. And the other one is related to complex geometry. And this is called B-model. Okay, so roughly speaking, on both sides, there are some kind of quantum field theory is infinite dimensional, and they're describing some kind of action on the mapping space. Let me say it this way. So, of the space of maps, in the A site, there is a particular type of action functional. Let me just say a model. I won't write it down. This infinite dimensional is very difficult to study, but nevertheless, at a formal level, you can do some kind of duality transformation, and you can do basically Fourier transform. Or some kind of thing related to T-duality to a different model. Again, it's going to be something on the mapping space from the sigma to another manifold, which is called a mirror manifold, and with a different action, different theory. Okay, so both sides are infinite dimensional geometry, and so far we don't have a rigorous description of both sides, either sides. I mean, in a particular at the original level. However, there is a trick which relates this model to geometry. It's so-called localization, because this model they're supersymmetric, and there is a version of so-called supersymmetric localization. It's very similar to, for example, like in this Atiyah-Bott localization formula, when you have symmetry of the manifold, then if you try to do integrations of the manifold, you localize to a fixed point. And this is something very similar happening here. And because of supersymmetry, this is localized to something simpler. In the A side, it localized to holomorphic maps. And we know for holomorphic maps, this becomes finite dimensional. And this becomes a version of like Gomov type theory of counting holomorphic curves. Okay, on the other side, on the B side, you can also do localization. And you may sometimes heard people saying that if you do localization in the B model, it localizes to constant maps. A constant map somehow sounds like much simpler, but this is not actually quite true. I mean, this is true if you do topological B model without coupling to gravity. But if you couple to gravity, you include a moduli space on the Riemann surface, then this is a little bit subtle. But anyway, let's assume something like that. I will explain to you later that this geometry of this localized stuff is quite different from the A side. But anyway, if you do this, you'll find some kind of Hodge type theory. Okay. Oh, by the way, I won't explain this process of localization. So if you are interested in, you can look at actually my lectures long time ago at Perimeter Institute, which is called Supersymmetry and Topological Field Theory. And actually, this is also available on my Bilibili account, which is it's called 量子轨道 at Bilibili. Okay, so just in case you're interested in. Now, there's actually different ways of describing both sides. Now here is like a string theory description. And usually we call this one like a worksheet theory. Literally, this one describes the mapping space and coupled to gravity, things like that. So we are describing something like that. And the domain of this map is called a worksheet. And on the other hand, there's a different way of describing this data, this idea from physics, as follows. So let me write it on this side. This is called stream field theory. And roughly speaking, this string field theory describes string theory in the language of quantum field theory. It's pretty precise. There's actually a pretty precise way of doing this, but let me be brief. I will just illustrate the basic idea. So describe the string theory in the language of quantum field theory. So here, the rough idea is the following. Now, we quantize string theory. You find some kind of like a quantized Fock space here, states, like either in this open closed string for the circle or open string for the interval. But anyway, from this string Fock space, so for every state here, basically we associate a string field. I'm going to call the same notation psi. And somehow the dynamics of the string propagating in such a way, and is going to be described by an action functional of the string field. So let's write it in such a way. It's called a string field action. So for example, you might describe the dynamics of string like that, like closed string. And for string field, it describes something like this. Okay. And there's actually a long history about string field theory, and this is like developed in extensively in different aspects. But now I will describe one particular development which is related to our discussion later. And this is the one I want to mention about the work of Zwiebak. In 1992. And Zwiebak described a general structure for closed string field theory. And he discovered the following, like closed string field theory is described by some action functional of string action. Which has the following property. First, it contains infinitely many of vertices satisfying some relations. So let me write in such a way, which contains infinite number of vertices. And this vertex is satisfied by a particular equation, which is called the B-Wien-Mast equation. And we will describe this B-Wien-Mast equation in the context of V-model later. And that's going to be one of the key objects that we're going to study. And in particular, if you look at genus 0 string field, I mean for closed string, then you will discover basically homotopy Lie algebra called L infinity algebra. And that's for the closed string field. This is pretty general. And later, like again, this construction is generalized to open string. So by Zwiebak in 1997, he basically extended this theory to open string and incorporating this open string field. By A infinity algebra. And when they are coupled together, they satisfy a version of open-closed quantum mass equation. And this open-closed quantum mass equation somehow was described in terms of the moduli of bordered Riemann surface. So again, we'll say a few words about it when we come to the discussion of open-closed B model. Okay. Now, so for the B model, for this side, and we're going to focus on the discussion of a B model from the string field theory point of view. And the B model usually is called a B-twisted topological string. Or it depends on whether you couple to gravity or not. Like usually people call this one topological field theory, and then when you couple to gravity, it's about a topological string. Again, there are many different ways you can look at B model and find some generalizations, extensions. For example, you can also do categories, categorical constructions, and blah blah. So I'm probably gonna more focus on this geometric aspect. So, as I mentioned, the B model somehow is localized around constant maps. So the constant maps is like everything shrink to a point, and you basically look at the quantum fluctuation around that point. Then this one becomes some kind of gauge theory on the target, like local theory on the target, glued in a way. So you find some versions of local string field. Action, which controls basically the effective theory. Now, so here's a rough picture. So originally you describe, say, a topological field theory in a B model by some dynamics like that. Then in the string field description, you localize to some constant map at some point. And then you have some kind of local interaction here, and describing the effective theory, and such that the original integral on the mapping space now effectively described by some kind of local functional. And that's the kind of thing we want to describe. So let me say a few words about some development for describing this action. So first, in the famous work of Witten in 1992, and he described the following, like actually both sides. Like he described a model, like say open string field, in terms of Chern-Simons theory plus some kind of instanton correction. He also described the B model closed string field theory in the same paper. This is the place he proposed this holomorphic Chern-Simons as the corresponding B model called open string field. We will describe this later. And it actually also speculate that the theory actually has to be UV finite. And I'll say a few words about what it means later. And now we know this is actually true. This is follows by a recent work, actually this year, by my former student Minhao Wang, and also Junrong Yan. And they find that basically shows this UV finiteness for this holomorphic theory in general. Now, this for the open string. For the closed string, this is a famous work by Bachetsky, Sakori, Oguri-Wafa. Actually, in two works, but I'm going to focus on the one on 1994. And nowadays, people call this basically BCUE theory. And he finds a description of beam model, closed string. And on Calabi-Yau threefold, as a particular gauge theory, and which they call Kodawa-Spencer gravity. So, roughly speaking, what this Kodawa-Spencer gravity describes is the following. And at the classical level, if you say, for example, study the equation motion, and this theory, this Kodawa-Spencer gravity, it describes the deformation of complex structure. And they focus on Calabi-Yau threefold. And by Calabi conjecture, Yau's theorem, and this leads to basically a family of solutions of a rich flat metric. So in particular, this leads to non-trivial solutions of vacuum Einstein equation. And that's for this Kodawa-Spencer gravity. And there are a bunch of more features about this theory, and this original BCUE theory. They proposed a cubic interaction. This is actually the leading cubic interaction. In terms of what, in terms of the string field theory of Chvábák. In topological beam model. And actually, there's a full theory of this one. I will come to this story soon. I mean, the full extension of this one that incorporates the full Chvábák solution. But nevertheless, from this data, there's another famous construction by Barnikov-Kontsevich. And they basically figure out the geometry of these polyvector fields, which are the string fields of this BCV theory, and find a general way to construct Frobenius manifold. It's a classical genus zero data of the B model in general for this topological field theory. So this construction of Frobenius manifold via the geometry of polyvector field. And we will talk about it pretty soon in the next few lectures. Okay. So now we really want to basically construct the full structure of Zivabak on what he predicted for general string field theory. And starting from this leading term given by this Petritsky, Sikori, Oguri-Vafa, we actually find an extension which allows us to talk about the same story on Calabi of any dimension. So this is in my work with Kevin Castello. And we find the full string action for topological B model on Calabi of any dimension, not only just Calabi of threefold, on Calabi of any dimension. And which also satisfy the full B-wave master equation. And we just call this this one BCV theory. This can be viewed as a generalized Kodawa-Spencer gravity. And so it can also incorporate open string. So again, in my work with Kevin Castello a few years later, we find a version of this B model open-closed. Quantum coupling. In terms of large N technique, and it's from this perspective we figure out a version of so-called twisted supergravity. So this is a kind of geometry of B model I will spend most of my lectures to explain this theory. Okay. Yeah, so far there's only some very brief descriptions, and I will discuss the story in detail. We have plenty of time, right? So before we move on to details, let me first fix my convention that's going to be used throughout this lecture, this mini course, and convention. I'm going to just write it for once, and I'm going to use it forever in this mini course. So I'm going to work with like gradient vector spaces, the category of gradient vector space. Let's say for a Z graded vector space V. I'm gonna write this notion like Vm to denote the degree m piece of this gradient vector space. And also, for an element here, let's say A, which lies in this degree m component, I'm gonna write sometimes called degree. Sometimes I'm gonna just write, for simplicity, this notion to say this one lies in degree m component. Okay? So another notion I'm going to use a lot is the shifting by degree. Say V is a gradient vector space. The shift by n is the following, like a degree shifting of the space in such a way that if you look at a shifted space, I look at the degree m piece. It's given by the degree m plus n piece of the original vector space. So geometrically, it looks like this. So originally, suppose it's a chain complex. This is like a gradient vector space. So this is my components in different degrees. So this is, I focus on this particular piece. Then this shifting by shift of degree by n has the following effect. You move the whole thing to the left by n units. So after you do this shifting, it probably lies here. So this is a shift by n. You can check. This picture is consistent with this notion. Also, I'm going to work with some constructions of tensors on like gradient vector spaces. So I'm going to use this notion, symmetric and symmetric tensor of my gradient vector spaces. This means the following. This means it's the n tensor quotient by this equivalence relation. Here, it's like A tensor B is equivalent to some signs, this Kourou signs, B tensor A. You see, like if both A and B are even degree, then this is a standard like symmetric tensor. But if for the gradient, but in the case of gradient vector space, you have to remember this this sign in a way. So when you switch these two, this is called Kourou sign, and this is called a gradient symmetric product. Another construction I'm going to use a lot is like so-called exterior product. This is also the generalization of the exterior product for the standard vector space, but to incorporate degree, this is like a graded pieces. So again, the same thing as like nth tensor quotient by a relation. Now this relation is given by an extra minus sign, the school symmetric relation. So this is an extra minus sign. This is called graded school symmetric product. Okay, so if you are not familiar with this notion, here is an extremely good exercise. And to show that if you take the symmetric tensor of the degree 1 shift of the original space, this is canonically isomorphic to nth exterior product. Now shift everything by degree n. So this means like if you shift the degree by 1, you basically turn everything like symmetric relations to skew symmetric relations. And this is not complete. This is not trivial. I mean, if I strongly recommend you to sit down and to try to figure this out. And again, I'm gonna use, for example, this notion. It's like symmetric functions, like polynomial functions. And sometimes I'm gonna write white hat for the completion. Like this, like formal power series ring. Okay. So finally, I need the following notion. So for a graded algebra, A, whenever I say write something like a commutator in this in some kind of graded operations, a graded algebra, this commutator, this always means graded commutator. So for example, this means like suppose I apply this one to like say 2 elements of A and B, then this literally means like A product B minus the cosine B product A. So this also applies to, for example, like the algebra of like linear operators on some kind of graded vector space and things like that. Okay. So finally, for a smooth manifold, X, I'm gonna write this notion to be like the space of smooth differential forms, and it decomposes into like different pieces. So this omega k is like smooth K forms. And we know for differential form, there's a natural operator of degree 1, which is a de Rham differential. This is a de Rham differential. And then we're going to work for, most of the time, work for like a complex manifold. Then in this case, my differential form has a decomposition into types, like say omega k is going to be decomposed into PQ forms, where P plus Q equals K. And my de Rham differential will also be decomposed into 2 types. D, one of them is called D bar, which increases the anti-holomorphic index by 1. The other one is holomorphic de Rham, which increases the holomorphic degree by 1. Okay, that's going to be the notation I'm going to fix along the whole course. Okay, so I think we're going to take a break, and we're going to continue next to describe this stuff in detail. Okay, thank you.